Okay, let's continue our discussion on anharmonic oscillator. So in the last class I have told you that diatomic molecules, okay, behave like anharmonic oscillators. Okay, they do not follow Hooke's law, right? So real molecules are anharmonic oscillator, and for anharmonic oscillator, two things which is very important. When L become very large compared to the equilibrium bond length, L is the bond length or the internuclear distance during stretching. When L become very large compared to L naught, what will happen? The bond breaks. Bond breaks. Okay, and if the two atom comes closer, that is during compression, L become very small compared to L naught. In this case, the potential energy, okay, behave like, or it appears almost like steep potential energy. Okay, so the potential energy curve for anharmonic oscillator in the case of one dimension, right? Suppose this is x equal to 0, right? How it will appear? In the case of simple harmonic oscillator, I have told you the potential energy curve appear like a parabola. This is for simple harmonic oscillator. But real molecules do not follow. Real molecules are not simple harmonic oscillators. Real molecules actually follow the anharmonic behavior, okay, or anharmonic oscillation, right? So how the potential energy curve exists for an anharmonic oscillator, right? When x become very large, that is when x positive means it is stretching. When stretching, if you stretch the molecule to a larger extent, what will happen? The bond breaks. Once the bond breaks, then you will get individual atoms. Then the potential energy of the total potential of the energy of the two atoms, total potential energy become a constant. Okay, and during compression, potential energy increases in a steep manner because when two atoms comes closer, the nuclei of the two atoms repel each other. Okay, therefore potential energy increases in a faster manner. Therefore, the potential energy curve, okay, appears like this. For compression, potential energy goes like steep curve. Okay, and in elongation, okay, and elongation, potential energy increases, and after a particular distance, what will happen? The potential energy or the bond breaks and potential energy become constant. Okay, so this red line indicate the behavior of real molecules. So this is called anharmonic oscillator. Anharmonic oscillator. Okay, real molecules actually follow this anharmonic curve. Okay, potential energy curve. Now listen. To fit with this equation, Morse gave a formula, an empirical formula for potential energy. The empirical formula is this. Last class I gave the potential energy formula, Morse potential energy equation or function. What's the Morse potential energy equation? Potential energy in one dimension is equal to equilibrium dissociation energy times 1 minus e power minus ax the whole square. Okay, dE is the equilibrium dissociation energy of the molecule in joules. A is the molecular parameter, okay, or it is a constant for a given molecule. X is the displacement. Okay, and using this potential energy function, if you solve the Schrodinger equation, right, we get, see, if you solve the Schrodinger equation, that is h psi of x equal to E into psi of x by what is the Hamiltonian operator? Minus h bar square by 2 mu, right, where mu is the reduced mass, into d square by dx square. This is the kinetic energy operator for one dimension, plus what is the potential energy? The Morse potential energy, that is dE into 1 minus e power minus ax the whole square. If you introduce, or if you take this Hamiltonian and if you solve the Schrodinger equation using perturbation theory, we get the expression for energy, okay, EV, where V is the vibrational quantum number. EV is equal to V plus half into hc omega E bar minus V plus half the whole square into hc xe omega E bar. This is the expression for energy, and we wrote the energy expression in wave number unit. This is in joules. Okay, this is energy expression in joules. If you want energy expression in wave number unit, in spectroscopy, conventionally we write energy in wave number unit, okay, because it has direct advantage with the spectrum, that's why. So the vibrational energy in wave number unit is given as V plus half into omega E bar minus V plus half the whole square into xe into omega E bar. So this is the vibrational energy, quantized vibrational energy for a diatomic molecule, okay, assuming the molecule as a Morse oscillator, that is, it follows the Morse potential energy function. Okay, here this is very important. Don't think that Morse potential energy function gives the exact nature of the real molecule. No, Morse gave an empirical relation, right, which is almost close to the experimental curve, but it is not exact. Okay, so that's the point you should keep in mind. But it is very close to the experimental curve, right? So this is the energy expression, and we found that in the last class we discussed the selection rule. Okay, what is the selection rule? Selection rule says that dipole moment of the molecule during vibration should change. Okay, dipole moment should change during vibration, right? This is the gross selection rule. And what is the specific selection rule? Change in vibrational quantum number should be plus or minus 1 or plus or minus 2 or plus or minus 3, etc., etc. All these are allowed values. Okay, so from this allowed values we can say that V equal to 0 to V equal to 1 is an allowed transition. V equal to 1 to V equal to 2 is allowed transition. V equal to 0 to V equal to 2 is allowed. V equal to 0 to V equal to 3 is allowed. Like that we have many transition possible. Okay, 0 to 1 is allowed. Why? 1 minus 0, you will get plus 1, which is allowed. 2 minus 1 is plus 1, that is also allowed. Similarly, 2 minus 0 is plus 2, that is also allowed, right? And these transitions, okay, are named, they have some specific names, right? The transition from 0 to 1 in the ground electronic state is what we call as fundamental vibrational transition. Okay, I'll write like this, FVT. In the last class I discussed all these things. FVT means fundamental vibrational transition. Then 0 to 2 transition is called first overtone transition, FOT, right? And 0 to 3 is called second overtone transition, and 1 to 2 is called first hot transition, right? These are all some specific names of the of these vibrational transitions, right? Then we also discussed that the energy required for the transition. Okay, what is the energy required for energy required for transition? Okay, this also we discussed in the last class. So what is the energy required for transition? For fundamental transition, that is 0 to 1. For fundamental transition, how much energy is required? That is nothing but delta G, and last class we derived it. The value is omega E bar into 1 minus 2xe. Okay, for fundamental transition, this is the energy required. Okay, similarly for first overtone transition V equal to 0 to V equal to 2, right? The energy required for transition is 2 times omega E bar into 1 minus 3xe, right? Similarly V equal to 0 to V equal to 3, it is called second overtone transition. What is the energy required for second overtone transition? 3 omega E bar into 1 minus 4 times xe, right? Similarly, what is the energy required for first hot transition? That is V equal to 1 to V equal to 2. Energy required for first hot transition is omega E bar into 1 minus 4xe, right? So these things we discussed in the last class, and remember these expressions. Okay, energy required for fundamental vibrational transition, energy required for first overtone transition, energy required for second overtone transition, and energy required for first hot transition. Okay, then here I like to give an important point, that Xe value is very small. Okay, Xe value is small, therefore 1 minus 2Xe, okay, since Xe value is small, 2Xe also small, so you can neglect this. If you neglect this, then this value is roughly equal to omega E bar. So energy required for fundamental vibrational transition is roughly equal to the equilibrium vibrational frequency of that bond. Similarly here, see 3Xe also very small, okay, compared to 1, therefore you can neglect this. So if you neglect, then this is roughly equal to 2 times omega E bar, right? See, energy required for fundamental transition is just omega E bar, whereas energy required for first overtone transition is twice omega E bar. That means this transition require low energy radiation, and this transition require high energy radiation, or it will absorb the radiation at low frequency, and this will absorb radiation at higher frequency. That's the meaning. Similarly, 0 to 3 transition is roughly equal to 3 times omega E bar. So second overtone transition will appear at higher frequency compared to first overtone, right? What about hot transition? Yeah, listen, if you see this equation and this equation, see here we have omega E bar, here also we have omega E bar. So in this case, I'll take the entire quantity. We are subtracting 2Xe from 1, whereas here we are subtracting 4Xe from 1. So definitely this value will be less. So energy required for first hot transition is less compared to energy required for fundamental vibrational transition. Okay, that means this transition will appear at a lower frequency compared to the fundamental vibrational transition. Okay, yeah, so keep this in mind, this is very important. Now, so these things we discussed in the last class. Now what I am going to do, what is the frequency of the spectral line? Frequency of spectral lines. Spectral lines. That is, at what frequency, okay, a particular vibration or vibrational transition will occur, or what radiation frequency is absorbed, okay, for a particular transition. Okay, say for example, let us first discuss the fundamental vibrational transition, first overtone transition, second overtone transition, etc. We'll discuss this first. Okay, first overtone, second overtone, and other overtone transitions. Other overtone transitions, right? At what frequency these transitions will appear in the spectrum? Okay, see, for this transition, the lowest vibrational number should be 0, correct? For fundamental, the transition occurs from 0 to 1, 0 to 1. For first overtone, transition occurs from 0 and reaches to 0 to 2, here 0 to 3. So in all these transitions, the initial vibrational state is 0. Initial vibrational state is 0. And what about the final vibration state? So I'll just remove that. Initial state is 0, and final state, let me represent that as V in general. Okay, 0 to V. For 0 to V transition, okay, what is the frequency, at what frequency this transition will appear. Okay, so frequency of radiation required for 0 to V transition. Okay, it may be 0. If V is 1, it is called fundamental vibrational transition. If V equal to 2, it is called first overtone transition. If V is 3, it's called second overtone transition, right? So in general, what is the expression for the frequency of any 0 to V transition? Okay, which is nothing but energy required for that transition, correct? Because we write energy in wave number. So frequency of the radiation that is absorbed for 0 to V transition is equal to energy required for that 0 to V transition. Okay, how much energy is required? Which is energy of the final state V minus energy of the initial state, that is 0. Okay, what is the energy formula? You know very well, V plus half into omega E bar in wave number unit minus V plus half the whole square into Xc into omega E bar. Okay, this is the vibrational energy for the Vth state, minus what is the vibrational energy for the V equal to 0 state, that is ground state. So wherever V is there, you put 0 here, you put 0. So if you put 0 here, 0 plus 1 by 2 is 1 by 2. So you'll get omega E bar by 2. And if you put 0 here, 0 plus 1 by 2 is 1 by 2. 1 by 2 square is 1 by 4. So we get Xe omega E bar by 4. Okay, Xe omega E bar by 4. Now let me simplify this. I'll multiply this by omega E bar. So we get V into omega E bar plus omega E bar by 2, and I'll expand this minus okay, let me keep this term as such for this step. Okay, I'll multiply this by minus, so I'll get minus omega E bar by 2, and here I'll get plus Xe into omega E bar whole divided by 4. Okay, now what I'm going to do, see here we have plus omega E bar 2, here we have minus omega E bar 2, they get cancelled, so we get V into omega E bar. Okay, now here we have Xe omega E bar, here also we have Xe into omega E bar, so I'll take this, take that quantity as common. So minus Xe omega E bar, I have taken this as common. So what we left with is V plus 1 by 2 square. V plus 1 by 2 square, if I expand, I'll get V square plus A square plus B square. 1 by 2 square is 1 by 4 plus 2AB 2 into V into 1 by 2, 2 to cancel, I'll get V. Okay, and here see I have taken minus Xe omega E bar as common, therefore we get a minus sign here by 4. Okay, see I am taking minus Xe omega E bar as common term, so here we will have V plus half whole square, and here we will have minus 1 by 4, so that if you multiply by minus, I'll get minus into minus plus. Okay, so plus 1 by 4 minus 1 by 4 cancel here, so what we get is V into omega E bar minus, see here in the inside bracket we have V square plus V term. If we take V as common, we'll get V into V plus 1. So I can write this as V into V plus 1 into Xe into omega E bar. Okay, this is the frequency for general expression for the frequency of radiation that is absorbed for 0 to V transition, for any 0 to V transition. This is the general expression. Okay, now what is the frequency for fundamental transition? If you want frequency for fundamental transition, wherever V is there, you put V equal to 1 here. So if you put V equal to 1 here, I'll get omega E bar minus, put 1 here and 1 also here. So 1 plus 1 is 2, so 2 into 1 is 2, you'll get 2 into Xe into omega E bar. Okay, and remember this general expression, which is very, very important. Okay, using this formula, okay, you can write the frequency of the first fundamental vibrational transition, and for any overtone transition you can write the frequency directly. Okay, so remember this formula. Okay, clear? Then similarly, what is the frequency, at what frequency first hot transition will appear? Okay, yeah, for that I am not going to write any general formula, because hot transitions and all we usually we don't prefer that. Okay, so I'll write frequency for first hot transition alone. At what frequency first hot transition will appear, which is nothing but energy required for the hot transition. What is the energy required for hot transition? Very simple, omega E bar into 1 minus 4 into Xe. Right? This is the frequency at which, or this is the amount of energy required, or this is the frequency which is required for the first hot transition. Okay, yeah. So we discussed the frequency of the spectral lines. Okay, so at what frequency the spectral lines will appear. So where, if I plot, suppose if I plot intensity in y-axis and radiation frequency in x-axis. Okay, so radiation frequency increasing from left to right. Right, listen, this is very important. At which where fundamental line will appear, where first overtone, where second overtone, okay, those things will appear. Right, fundamental transition appear at a frequency which is roughly equal to omega E bar. Okay, I have told you already, which is closely equal to omega E bar. So this is transition correspond to 0 to 1, fundamental vibrational transition. Then first overtone transition will appear, okay, twice the omega E bar, roughly twice the omega E bar. So this is the first overtone transition. Similarly, second overtone transition will appear at thrice times, 3 times the omega E bar. Okay, like that it goes. Okay, so remember, after fundamental transition, okay, overtone transitions will appear, or I can say in the other way, overtone transitions appear, okay, in the higher frequency side of fundamental transition. What about the hot transition? Hot transition and fundamental transition, they appear closely, because for fundamental transition, okay, the energy required is omega E bar into 1 minus 2 Xe. We subtract only 2 Xe, whereas for first hot transition we subtract 4 Xe, omega E bar into 1 minus 4 Xe, correct? Anyway, Xe is very small quantity, so 2 Xe, 4 Xe, that difference is very, very small. Therefore, fundamental vibrational transition and the first hot transition, okay, will appear very, very closely. But first hot transition, okay, will appear before the fundamental vibrational transition. Right? So this is how the lines will appear in the spectrum. So we get many lines, okay, for fundamental, for first overtone, second overtone, third overtone, etc., etc. Right? So the unharmonic oscillator, right, could explain, right, the reason for the appearance of many lines, okay, in the spectrum. Right? Then what about the intensities of the spectral lines? Intensities, right? Intensities of spectral line. Intensities of spectral lines. Okay. Which line is more intense? Which line is less intense? Yeah. Intensity of vibrational spectral lines. Okay. In the case of vibrational spectrum, intensity is directly proportional to square of the modulus of transition moment integral. Okay, square of the modulus of transition moment integral. Okay, and keep this in mind, this is very important. Transition moment integral, modulus of transition moment integral for fundamental transition is very, very high. This value is very, very high. This integral value is very, very high. Therefore, fundamental transition always appear with the high intensity. Then transition moment integral, modulus of transition moment integral for first overtone. Okay. Then modulus of transition moment integral for second overtone. Right. Like that, many overtone transitions will appear. Then we get transition moment integral for hot transition. Okay, remember, hot transition will appear with a very low intensity, right? So keep all these things in mind. Okay, so the intensity order is this intensity order. Okay, always, right? Intensity for 0 to 1, I'll put I for 0 to 1 transition is very, very high. Intensity for 0 to 1, that is fundamental transition. Then intensity for first overtone transition. Then intensity for second overtone transition, right? Like that, other overtone transitions intensities will decrease. Then you will get intensity for 1 to transition, that is first hot transition. Okay, so in the spectrum, how do these lines actually appear like? Let me just draw and show you. So in the spectrum, if we plot intensity in y-axis and frequency of the spectral line in x-axis, remember, first hot transition, that is 1 to 2 transition, appear with a very, very small intensity, very, very low intensity, whereas fundamental transition will appear with a high intensity. This is fundamental. Then first overtone 0 to 2, then second overtone 0 to 3, then next overtone, that is 0 to 4, like that it goes. Okay, so which line is the highest, the most intense line in the vibrational spectrum of a diatomic molecule? Is that the fundamental vibrational transition? Okay, or the spectral line correspond to fundamental vibrational transition. That is the most intense line in the vibrational spectrum of a diatomic molecule. Okay, yeah. Now, so using anharmonic, using Morse potential energy function, yes, it is possible to explain the appearance of many lines in the vibrational spectrum of a diatomic molecule. But if you go to high resolution IR, if you take vibrational spectrum using high resolution spectrometer, in high resolution, each line here, let me take a fundamental line for reference. Okay, the fundamental line in low resolution, it appear like a single line. But if you take the spectrum for a diatomic molecule under high resolution, okay, each line, for reference I have taken fundamental line here, the fundamental line appears, okay, with many lines like this. Okay, it appears with many lines. It appears actually like this. Okay, so each line will appear with many lines in the spectrum. Okay, so what is the reason? So these are the lines which appear very closely for fundamental transition. Like that, we will get many lines for first overtone, second overtone, but intensities of these lines are very small, so we usually neglect, or we usually discard the fine structure of the other transitions, right? Overtone transitions and all. Okay, we call this as the fine structure. Okay, yeah. I stop here. What we are going to do in the next class is that how to explain these lines. Okay, each line in the spectrum, right, under low resolution IR spectroscopy, right, will appear with many lines in high resolution. This you cannot explain using that just Morse function. Using just Morse function, you cannot explain all these things. So what we are going to do is, in the next class, we are going to see or we are going to incorporate, okay, rotational motion, right, with the vibrational motion, right? See, when molecule vibrates, the vibrational energy is so high, so vibrating molecule, right, vibrating molecule not only vibrate, it also execute rotation. Okay, so in the next class I am going to couple the vibrational motion and the rotational motion. Okay, so if you take the vibrational motion and rotational motion together, right, can we explain, right, these fine structures, right, of lines that appear in the IR spectrum? That's what we are going to see in the next class. I stop here.